Hello everyone and welcome back to Advanced Robotics. Today is day 4, so we're going to be talking about wiring and electronics. We're going to go over the REV Hub and why it's so important, as well as different types of wires, sensors, and other electronics, along with some real-world examples once again on Masquerade's robot. So what is a REV Hub? REV, as I've mentioned before, is a vendor endorsed by FTC that sells various hardware and electronics. REV technically sells two different kinds of hubs, the expansion hub and the control hub. However, the control hub just became legal for use in Florida this year. So we're going to focus on the expansion hub because that's what most teams rely on. The REV Hub distributes power, receives data from sensors, and relays instructions to motors and servos from the robot controller, which I'll talk more about later. REV Hubs also have a built-in IMU, or inertia measurement unit. This is an onboard sensor that detects distance, direction, and rotation. It's possible to connect multiple REV Hubs together using a special kind of wire. However, teams are only allowed to have 2 REV Hubs on their robot. Power comes into the robot from this battery, right here. The power from this battery then goes to this power switch, which when turned on sends the power to this power bus. It is that white rectangular part right there. Multiple wires then come out of this power bus and deliver power to whatever needs it. Mainly this REV Hub right here, and this one right here. There are 2 main kinds of signals, analog and digital, that a sensor can produce. The value of an analog signal can be pretty much anywhere within a certain range of numbers, which is usually based on the type of data you're collecting. Digital signals, on the other hand, are only able to produce 2 different values, 0 and 1, which usually correspond to off and on. Encoders connect to axles, and are able to measure various metrics based on their rotation. Many newer motors have encoders built in, although for a mechanism drivetrain these wouldn't be very useful. Because autonomous relies heavily on data from the robot's position, encoders are essential for scoring the maximum points possible. Mechanism drivetrains strafe left and right by moving certain wheels forward and other wheels backwards simultaneously. While this is useful for mobility, encoder measurements directly to these wheels and motors are going to be inaccurate compared to where the robot's actually moving. In order to combat this, we have 3 passive omni wheels, here, there, and there. One each on the left and right, and one in the back. These measure actual distance that we're moving in any of these 4 directions. Because of the rollers on the omni wheels, if we move left or right, our forward and backward measurements won't be affected, and vice versa. As I've mentioned before, servos are different from motors in the fact that they rotate to a specific angle, which is specified by various data points, such as sensors or buttons on a controller. A servo programmer is used to calibrate and test servos. Different servos may have different bearings. For example, 0 degrees may be at a different location from one servo to the next, and it's important to account for these differences, specifically in programming, in order to prevent unwanted damage or movement. There are several different kinds of sensors, and each sensor has a certain criteria that must be met to send data back to the REV Hub. For example, a touch sensor sends a signal as long as the button is being pressed. These are usually used to test whether or not the robot is coming into contact with something in its outside environment. Limit switches are like touch sensors, but instead of a button there's usually some sort of lever or prong, and limit switches are usually used to test the location of a part inside the robot. A color sensor detects the presence of red, green, and blue light, and uses the mixtures of these measurements to infer what color is being shown. For example, if there's a bright red and blue light but no green, the sensor is most likely looking at something purple, which it will then relay back to the REV Hub. Cameras collect and send video data, which can be very useful, but requires an extra USB hub as well as advanced programming to be used effectively. There are 2 types of legal distance sensors in FTC. One is the optical sensor, which uses an infrared laser. It's very accurate, but it only goes up to about 2 meters. The ultrasonic sensor uses sound waves, almost like a bat or a dolphin using echolocation. They can reach up to 4 meters but are not as accurate as the laser. Most teams who need a distance sensor use an optical one, because in most cases accuracy is much more important than range. While the REV Hub has a very high device capacity, it's only able to connect to specific wires, which can be a challenge if you're using sensors or servos from many different vendors. To resolve this issue, many vendors sell conversion kits, which have one side of the wire that they use, another side of the wire that goes into the REV Hub, and a small chip called a converter in the middle. Vendors also sell extension cables, which are used for more length when parts are too far away from each other. A variety of methods are used to manage wires and keep them out of harm's way, including sheathing, zip ties, and braiding. If wires get tangled or torn in motors or servos or other parts during a match, that could end up being catastrophic for the team. So obviously you'd want to minimize the chance of that happening. Not to mention the fact that organized wires just look way cooler. As you can see here, this is one example of wire management with the zip ties right there to hold this wire here up. If it was free to just move around here, it could get stuck in the motor or one of the pulleys or the lift right here. And during a match, that obviously could cause a lot of problems. We also have wire sheaths right here for ones that are on the outside that need a bit more protection. This is just kind of an outer layer to protect the wires inside from any sort of damage. We also have one right up here to carry the more durable wires, like the power wires. The power cable gets cut, and that's pretty much game over. Each team has a pair of two phones, the robot controller and the driver station, which need to be configured properly for the robot to be able to do pretty much anything. The robot controller stays on the robot, as the name would imply, and carries out the instructions given to it by the driver station. The driver station stays with the drivers outside of the field, and contains the programs and device configurations. Device information must match up in both the program and the configuration, or else the robot controller won't know which part of the robot to send the instruction to. If everything's running smoothly, the robot controller phone should look something like this, with no red or orange error messages. This white USB hub right here is what allows the REV Hub to connect to the phone, both receiving data and power. The driver station phone both shows battery power and allows teams to choose various programs, either autonomous or teleop, depending on what's downloaded. The robot is controlled using these two controllers, which connect to the phone using this USB hub. And that in turn gets power from this battery pack. And on that note, we're going to wrap up day 4 of Advanced Robotics. Day 5 is going to be our last one, and it's going to focus mainly on programming and actually driving the robot. Thank you all once again for watching, and have an amazing day.